Welcome everybody to Group 5's project presentation for the optimization of the scissor jack by Daniel Belfort, Adam Heinz, and Ann Fahey. For our problem statement, we wanted to design the car jack to reduce the amount of torque applied to rotate the screw, but also keep in mind the effect this has on the cost of its production. This was done to balance the user experience or ease of using the car jack and the producer's material costs. From our literature review, we were able to find various ways to optimize the scissor jack. The main one being a change in the material in use. We're also using different materials for different components of the car jack. We were able to learn the most critical components for failure, some of the reasonable ranges for constraints, and some of the most common materials and their material properties from studies that have been done in the past. For problem formulation, we came up with two conflicting objective functions, the first being mu1, representing the torque required to rotate the screw, and second, mu2, the volume of the car jack. As you can see on the right, there are many variables that are used. Many are different lengths, areas, or radii of the components of the car jack. Also, different weights and final heights of the car jack must raise, but also mechanical properties like Young's modulus that will have to do with the strength of the material used. So for our constraints, many came from different force equations that we knew had to be true. The first one here representing the sum of forces in the y direction that we know must equal 0. The second constraint is a constraint for the weight of the car that we will know the car jack must be able to tolerate. The third constraint on this page is the force of the spring. And finally, we have the final height of the car that the car jack must raise. Continuing on with some of our constraints, we have different lengths, areas, and radii that are bounded that we found numerical values for during our literature review. Finally on this page, we have Euler's buckling formula, which will have to do with the strength of the car jack. Finally, we have some more constraints to make sure our objective function is positive, some more constraints on the length of the radius, and then finally some equality constraints that defines the coefficient of friction and also the pitch of the screw. During our modeling process, we knew that we wanted to use an epsilon constraint method. This is due to its robustness and its ability to detect convex Pareto frontiers. We also made many assumptions during our modeling process, the major one being that there's no dynamic forces at play, that the torque is being applied slow enough that there's nothing else acting on the car jack. We also assume the car jack is level, and our final assumption is that all the four different lengths of the car are all equal. The four components that make up the car jack are all equal and all the same. There were several changes that we made throughout our modeling process. The first being that we incorporated a changing bar length. This increased the complexity and added conflict to our objective. We also added bounds to our lengths and different radii. This was to come up with more realistic values. And we also made changes to make sure our objective function was more realistic. There was also several sources of error that we could identify during our modeling process. The main one coming from this simplification of the car jack. Our car jack, we assume to be 4 different components of equal length with one power screw that is used to raise it. So from this simplification, there are a lot of assumptions and different things that are not considered. So with all this in mind, we have our Pareto frontier for our car jack design, with mu1 on the bottom representing the torque required to rotate the screw, and mu2 on the vertical axis representing the volume of the car jack. And on the right, we have our optimal design point.
So now for the code portion of the project, we see here that we deal with 3 files. First one being the main file, then the objective function file, and the third one where we define our constraints. In the main file, we can see that we have some definition of our constraints, our starting and lower bound points. But most importantly, we see here this for loop, which is run the amount of design points that we want to obtain, which are 20. And we can see that we call this fmin_con optimization algorithm, which we get our objective function from, as defined here. We can see that it's defined only as mu1, our first objective function, since the second one is used as a constraint per the definition of the epsilon constraint method. Also in this constraint function, we define some constants. We define our first and second objective function, and these inequality constraints explained earlier, additionally to the equality constraints. So as we run this main function file, we can see different values of x vectors appearing, which are the different possible solutions to the problem, both traded off between the first and second objective functions. And we can see here the Pareto frontier as seen earlier, where all of these points lay, and which also lies the optimal point that we mentioned earlier. Thank you very much. I hope you enjoyed this explanation of our project.